Hello everyone. Sorry I couldn't make it to class today. I'm just downstairs in the gym for the grade 9 girls volleyball playoff game, so I'm hoping to be back before the end of the period to let you know how we did. So previously we looked at ionic compounds and polyatomic compounds yesterday. Today's focus is going to be on something that's called molecular compounds. So nonmetals can obtain a full valence shell, the outer shell, in two different ways. So what this can do is it can gain electrons to form anions, just like we looked at for ionic compounds. It can also share electrons with other non-metals. Okay, so in molecular compounds, that is where we have one or more non-metals bonding together. So the molecule is going to be a stable particle made up of atoms, and these are joined by bonds that we call covalent bonds. Okay, so once again, this is where you just have one or more non-metals. There's no more metals in molecular compounds, and they're sharing our electrons. So what does that look like? Let's say you have a non-metal such as fluorine. So we have a non-metal and a non-metal. So we're going to draw the valence electrons for fluorine. It is going to have 7. So we're going to draw 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and 7. Now because these are two non-metals, you can think about them that they're being very similar. Think about them as siblings. Okay, when they're the same, they're going to want to share with one another. So what's happening is that these single electrons will be shared. So this fluorine will have 1, 2, 3, 4, 5, 6, 7, 8. So that will be stable, have the full octet. This fluorine will have 1, 2, 3, 4, 5, 6, 7, 8. So this will also be stable. So instead of writing this right here, how we represent that is just simply with a straight line connecting the two. And then we can just fill in the valence electrons around it. Okay, so what this line means is that the electrons are shared. So in this bond here, which we call a covalent bond, so the smallest part of this is called an electron pair. When we have these covalent bonds, you could have single bonds that look like this. Another example is H2O or water. How that looks as a molecule is you have one oxygen and then you have hydrogen that look like this. So because there's these single lines, that's what represents a single bond. You could also have double bonds. So an example of this is carbon dioxide. So there's one carbon and 2 oxygen. How this is sort of quickly drawn is you have the one carbon, you have an oxygen over here, and you have the second oxygen over here. So how this is bonded is with these two lines, and a triple bond. An example of this could be carbon monoxide. So that would be the one carbon, you would have 3 like this, and simply just bonded to that oxygen. Okay. There's also the possibility to have quadruple bonds, but it's very rare, and we're not going to see that in our class. So the number of covalent bonds a nonmetal needs to form the stable molecule is something called a combining capacity. A combining capacity. So for example, if we take a look at carbon, we know that carbon, and looking at a periodic table, is going to have 1, 2, 3, 4 valence electrons. So this has the capacity to bond with something else, as well as this, as well as this, as well as this. So in this case, our combining capacity for carbon is going to be 4. If we take a look at chlorine, chlorine is going to have 1, 2, 3, 4, 5, 6, 7 valence electrons. So it has the capacity of this one singular electron to combine with another atom. So this combining capacity is only just 1. So next we're going to take a look at actually naming these molecular compounds. So again, the first thing you should always identify is, do you have a non-metal and a non-metal? Once you recognize that you have this, we're then going to follow this naming convention here. So in molecular compounds, we have a prefix that is used. So that's what goes in front of our word. Okay? And this indicates the number of each atom that is present. Okay? So for example, when there's one atom, we're going to use this prefix of mono. 2 di, 3 tri, 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, and 10 deca. So as an example, if we have something like CO, okay, we call this carbon monoxide. Since we have CO2, we write this using the carbon dioxide. The one rule you must keep in mind is that we're going to omit, or we're not going to use the prefix mono for the first element in the compound. So for example, when we have something, you see we have 1 carbon and 1 oxygen. So the name for this is going to be simply just carbon monoxide. We do not write this as monocarbon monoxide. Okay, that's just not the proper naming convention. You'll also notice that we don't write it as monoxide, because when you put these two O's together, it's going to make that oo sound, which is just incorrect. So with oxygen, you're going to notice through practice, okay, that we sort of just omit that O. So in this case, it's your carbon monoxide. If I just go up here really quickly, you see CF4. That's going to give us carbon tetrafluoride. Okay, we have something like PBr5. That's going to give us our phosphorus, not monophosphorus. We simply just write that element phosphorus penta for 5 bromide. Okay, so these are just some of our naming conventions for molecular compounds. There might also be some molecular compounds that are more readily recognized by their common names. So for example, H2O, you might think is dihydrogen monoxide, but we simply call that water. O3 is simply ozone, NH3 is ammonia, CH4 methane, and H2O2, instead of dihydrogen, dioxide, we have this common name of hydrogen peroxide. So this is what, I'll put this in a set of brackets, but this is that common name that you would use for this. So writing molecular formulas, we're going to follow these following steps. You're simply going to write the symbols of the elements, and then you're going to write the subscript for the number of atoms, again, represented by the prefix. So when you have, again, molecular formulas, you're going to identify whether it's a nonmetal, okay, and a nonmetal. So for this case, we have diphosphorus pentasulfide. If you look at these prefixes, di means 2. So if it's diphosphorus, we're going to have P2 pentasulfide. Sulfide is your sulfur. Since we have pentasulfide, we have 5 sulfur. So diphosphorus, 2 phosphorus, pentasulfide, 5 sulfur. Okay, another example over here. You have sulfur trioxide. That's your sulfur element, and that's your oxygen. Since this is just sulfur, it tells us there's only one of them. If it's trioxide, that tells us there is 3. Okay, if we look at carbon dioxide, it just tells us carbon. So we're simply going to write just that C. If it is dioxide, oxide tells us it's oxygen. The di is number 2. Okay, next we have phosphorus trichloride. Since it's just phosphorus, we have P. Trichloride, this chloride is chlorine. Trichloride, just like a tricycle, is going to be 3. So we have PCl3. Sulfur hexafluoride. Sulfur, we can write as just S. Fluoride is your fluorine. Hexafluoride, think about a hexagon. A hexagon has 6 sides. So we write that 6. So again, sulfur hexafluoride, SF6. Okay, and then our last one here, we have nitrogen monoxide. So nitrogen, it's simply just going to be N. Oxide is your oxygen. If it's monoxide, we simply have 1. And again, remembering from last time, we don't need to write those subscripts of 1. They're just going to be invisible. Okay, so just to recap, you're going to write the symbols of the elements and then write the subscript for the number of atoms represented by these prefixes. So the next one we're going to do here is writing the names of these nonmetals. Okay, so you're going to write the name of each element. You're going to change the ending of the second element to "ide." You're going to use the subscript value, okay, these right here, to determine the appropriate prefix, and then you're going to write the prefix in front of that appropriate element. So let's take N2O. We know that N is nitrogen, and the O is our oxygen, which we changed to oxide. Since there are 2 nitrogen, we write this as dinitrogen. 1 oxygen, we write that as monoxide. Again, you don't write it as because again, that would be monoxide. So we just omit that second O beside it. Okay, so let's try a couple of these examples together. Okay, so we got bromine and iodine. Okay, you got a nonmetal and a nonmetal. When you see that, that's where you think back all the way to this chart here of all these prefixes. So now we know it's going to be molecular, and we're going to be using those prefixes. Okay, so if we have bromine, there's only one of them. We do not write monobromine since it comes first. But since there is an iodine and there's only one of them, we write this as monoio, and we change the ending to IDE. Okay, so bromine monoiodide. Okay, we change that IDE. If we take a look at the next one, we have xenon and fluorine. Both of these nonmetals. Since there's one xenon, we can simply just write it as xenon. Fluorine, we're going to change to fluoride because there are 4 of them. The prefix for 4, if you go back to your table, it's going to be tetrafluoride. Okay, next we have N2O4. Both of these, nonmetal and a nonmetal, nitrogen and oxygen. Since there are 2 nitrogen, we're now going to write this as dinitrogen. This is oxygen. Since there's 4 of them, we're going to write this as tetroxide. Okay, you might think this would be tetraoxide. But again, oxygen is special. We don't put these sort of vowels, the A and the O, beside each other, just because, again, maybe the scientists who determined this thought that sounded a little bit weird. So that's where, in the case of oxygen, we just get rid of that A and we call this dinitrogen tetroxide. Okay, if we look at H2O, well, just by knowing that, the common name is going to be water, but this can also be referred to as, since there's 2 of them, there's 2 hydrogen, so we call this dihydrogen. There's 1 oxygen, so we write this as monoxide. We have carbon and fluorine, 2 nonmetals. There's only 1 carbon, and there are 4 fluorine. Again, 4 is our tetra. So we have tetrafluoride. SO2. S, there's 1 of them, so that's our sulfur. There are 2 oxygen, so we use the prefix of dioxide. P2O5, both of these nonmetals. There's 2 phosphorus. Diphosphorus. There are 5 oxygen. So we actually write this as pentoxide. You might think this would be pentaoxide, but just by having that A and that O, it's just not the naming convention for oxygen. So oxygen's that one exception. Then we say this is diphosphorus pentoxide. Okay, and then the last one here, we have 1 nitrogen. Again, we don't say mononitrogen. We don't need the mono for the first element. We call this nitrogen. There are 3 chlorine. Our prefix for 3 is tri. And instead of chlorine, we write this as trichloride. So the last component of this lesson is something that is called the diatomic elements. So if any of these elements listed below are free, that is that they're alone, they pair up and they're written with a subscript of 2. Okay, so diatomic, they exist as 2 together. So the acronym to remember this is called Hofbrinkel. So we have H, O, F, B, R, I, N, and C, L. So if you can remember this acronym, okay, this tells you what elements exist as diatomic elements. So for example, this H represents hydrogen gas. So hydrogen gas will have the formula of H2. O is the oxygen gas, which is O2. This fluorine gas is F2. Bromine is Br2. The iodine is the I2. I'm so sorry, it looks like I forgot the nitrogen. So maybe we can just add that up here. And that, as I'm sure you can see, is going to be N2. And then your Cl in your Hofbrinkel is going to be chlorine gas, which is Cl2. So that concludes our lesson for today. Thank you all for watching.